Okay, good morning everybody. I'm Francesco Topputo from Politecnico di Milano. I'm presenting the LUMIO mission concept, which stands for Lunar Meteroid Impact Observer. We are quite a bunch of people. This project is funded under the ESA 2017.A.2.1 number 4, which framework that was mentioned in the previous session by the worker. So I'm presenting the work on behalf of all of the LUMIO team, and the work is still in progress. Actually, we are in the first few weeks of detailed analysis, because we kicked off officially as of the 1st of May. So it's still the first work of the first month of work, and therefore things are changing on a daily basis. And for this reason, I cannot be specific in some particular items. So this is what we want to do. LUMIO is a CubeSat that has to be placed at Earth, Moon, and 2 in a halo orbit on the translunar equilibrium point, and shall observe the full disk of the lunar far side to detect impact flashes that are the flashes that are emitted whenever a meteoroid impacts the lunar surface. This would provide a lot of information to study the meteoroid models traveling the Earth in space, to quantify the hazard for next either human or robotic exploration of the moon, and maybe in a quite a longer term to pave the way for a lunar situational awareness program. We have the Lunar CubeSat is, as I said, at L2. It's the assumption of all of the studies that the CubeSat is released from a mothership when already the two of them are in lunar orbit, and we'll see the details later. So why going for this science investigation? As you know, the Earth-Moon environment is continuously bombed by meteoroids, which burn whenever they cross the Earth's atmosphere. But fortunately or unfortunately, the Moon doesn't have such a protective blanket, and therefore the impact changes directly on the lunar surface. This can be, of course, this has a huge impact on the evolution of the surface of the Moon. And whenever you have an impact with the lunar surface, there is a production of a seismic wave, the excavation of a crater, and the generation of an impact flash. Because the kinetic energy of the impact is so high, it can be up to 70 kilometers per second of relative velocity with respect to the Moon. So even a small rock has a huge kinetic energy, and it's so high that there is a generation of flash in the visible range. So we want to do this kind of, therefore, since the flashes are emitted, this is the only, let's say, viable option to detect meteoroid impacts with the Moon, because otherwise you have to have either in situ measurements with seismographers, or you have to take many pictures of the lunar surface and to compare each other to discover the creation of new craters. So having a constant survey of the lunar surface is deemed the only viable option to detect such impacts, and therefore there are ground-based campaigns which are conducted, for instance, at NASA Marshall, that monitor for obviously the lunar near side, but they are biased because of the presence of atmosphere. They are constrained by the weather, and they are restricted by the geometry, in the sense that you can only monitor the near side, and by illumination constraints, because you want to detect the flash when this occurs on a dark region. So there are a lot of opportunities with LUMIO. The first, as I said, is the science investigation, because we can perform continuous and high quality observations of the lunar outside, and with these products that we can generate, we can validate the solar system models, we can investigate the impact physics and the impact model in order to understand the nature of the factors, and we can contribute to lunar seismology, dust exosphere, and stratigraphy, because by quantifying the amount of impacts, you can also validate the model through which the lunar regolith, the upper layer of the lunar regolith, gets remixed now it's believed to occur every 80,000 years, thanks to new observations from the lunar reconnaissance orbiter. And of course, you can complement Earth-based observation. But there are also a lot of opportunities for what concerns the exploration, because flying a CubeSat into lunar environment is something that has never been done so far. We will have a number of CubeSats, as we saw this morning in the EM1 mission, but it's still a challenge from the engineering point of view. You can realize an outpost at L2, which can again pave the way to future implementation of novel concepts, such as the data relay with lunar far side, for instance. You can test orbit control with CubeSat, and as I said, flying beyond the LEO, and start a program to monitor the Moon in the framework of the Lunar Situational Awareness. What do we want to get from the scientific? As we said, the flashes can be detected in the visible spectrum, so we have to cover the lunar outside, and this shall work either during the meteor showers that occur 4 times a year, or during the sporadic impacts that can happen every time during the year. And our science products should deliver the spatial and the epoch, the location, the geographical location of the Moon, and the epoch of the event, the intensity of the flash, and we can deliver either all of the images or a portion of it. There is still a discussion on this, but for sure the pixels containing the event should be delivered. As constraint, we have to observe the full Moon disk, which is an added value of having high quality observations from space. The flashes should be detected in the dark portion of the lunar surface, and we have to have an exposure time that is higher than the typical duration of the flash, and the detector should be sufficiently, of course, sensitive to have a signal-to-noise ratio that allows to detect the occurrence of Moon. To do this, we are designing this LUMIO cam, which is a camera that builds up the previous heritage of Leonardo, which is one of the partners of the consortium here. I have dedicated slides on this. It's very sensitive, and it takes a number of images per second. Now we are targeting 3 frames per second. We have a spatial resolution of 3.4 kilometers per pixel, and we have a field of view of 3.5 square degrees, which means having the full Moon at 60,000 kilometers far from the center of the Moon. So we are targeting a signal-to-noise ratio at a magnitude at least of 6 or brighter. From a preliminary computation, it's evident that we cannot store images on board, because otherwise the amount of data skyrockets, and actually we have also a very tight constraint for communicating with Lunar Orbiter. So we are implementing an onboard payload data processing strategy. The rationale is that we keep we keep acquiring the images and we process them on board. We throw away all of the images without any events on that, and we save only those showing the occurrence of an impact within it. The mission analysis uses a state-of-the-art, let's say, approach, because LUMIO is released into a 200 times 15,000 kilometer, 50 degrees inclination with respect to the Moon. And we have a transfer to the grid, which are the main mission phases. The operative orbit has been selected as an L2L orbit because we have a permanent full disk observation from there. We can complement in this way the Earth, the ground-based observation both in space and time. In space because we take the images of the far side. In time because the surveys are done exactly as the opposite time when the ground-based observations are done, because when we have that side of the Moon, that side of the far side, you cannot take surveys from the ground side, and vice versa. It's easily accessible from this release orbit, and both the Earth and the Moon are always visible, which paves the way to perform some experiment for, as I said, for data relays. And maybe the most interesting item of this orbit is that you are locked in the 2-to-1 resonance with the synodic period of the Sun-Earth-Moon system, because the period of this orbit is 14.8 days, and the synodic period of the Earth-Moon-Sun system is 29.5 days. So every 2 revolutions you have the geometry that is always repetitive. So this eases the operations and so on. The transfer phase is divided into 2 maneuvers. We have a plane change maneuver from 50 degree inclination to 28 degrees, and once on this orbit, we perform a manifold injection maneuver, which aims at targeting a piece of the stable manifold associated with the L2 halo orbit. And after the impulse, you let it go, and the by itself reaches the L2 halo. We are targeting 1 year of operation, which means about 20 meters per second of delta V for station keeping, plus 5 meters per second margin. So we are at about 200 meters per second of delta V. Other options are being considered depending on the injection orbit. So this is still a work that is in progress. One of the major challenges of flying a CubeSat at L2 is autonomy, as was mentioned this morning. We cannot rely, by statement of work, on radiometric measurements. So navigation is an issue here because we don't have any GPS, of course. And we are studying to use the same payload to navigate as well. So we want to do full disk optical navigation. It works in this way. You take an image of the Moon, you get the terminator plus the line that discriminates the illuminated and the dark side. Then you reconstruct the terminator and you try to fit this into an ellipse. Of course, you know the epoch at which you took the image and the ephemeris of the Moon at that epoch, because you store them on board, and from this you can solve for your position with respect to the center of the Moon. This is how the okay, this is how it could work. This is just a sample orbit, sample circular orbit around the Moon, and in 20 days. You have the illumination that is changing, and you can see that you can have this is simulated by using the Pulse Ray software and SPICE that we are using. And you can have kilometer or up to 10 kilometer accuracy, which is not bad at all. We're flying there without relying on any radiometric measurement. Of course, when the illumination is below some percent, the error degrades, which is at the beginning and at the end of this simulation. But we are also fully aware of this. For what concerns the power, we have for what concerns the overview of the space segment, we have a 12U CubeSat, which is 2 by 2 by 3 units. We have deployable deployable and now some tracking solar arrays. As I said, it is changing daily. We used to have fixed wings solar arrays, but now we are starting out to have this tracking design because we have a quite steady power production profile, which eases the definition of the duty cycle there. We have of course propulsion because we have to impart at least 2 impulses plus the station keeping at L2, and we are investigating for using 4 VACO green monocovalent thruster plus an option to have water propulsion to perform the station keeping, but now option 1 is still ongoing. We have LUMIO is already margined 23.9 kilograms, which fits the requirement of having the 24 maximum kilogram platform. And we are elaborating, of course, on ADCS, telecom, thermal, and everything. I wanted to use my minute or couple of remaining saying that we are designing, we are performing this project by using the ESA's OCDT, Open Computer Design Tool, which can be, maybe I advertise ESA CDF saying that can be requested upon application. It's very useful. All of us are using this remotely, so we are working remotely, and we have weekly, let's say, telecoms, weekly workshops to just update the data on there. This is the team that is part of LUMIO. We have 3 universities, 2 companies, and the University of Arizona from the United States. The rationale of this is that the universities take care of the science investigation, the companies take care of the science implementation, Polytechnico and the University of Arizona take care of the mission analysis and operation, and TU Delft, the PFL, building upon their previous experience on university CubeSats, take care of the distributed CDF and the system design. We are having a 2-day workshop in Milan this September 11 and 12 that we will present the preliminary results that we have before the final submission, which will be at the end of October. So we want to have roughly a couple of months to, let's say, adjust some pitfalls that would arise during this workshop. So the workshop is open to people that can be interested in attending. If you're interested, you can contact me at this address. And we are finalizing the design by the end of October because the 1st of November, I guess, we have to deliver the final report. And that's it from my side.
Thank you very much. One quick question. Reddy, thank you take this comment. A quick question. Did you consider trying to do a similar mission, hitching a ride on a mission that's going to L2 directly? Can you do it, therefore, even cheaper and easier because you don't have the propulsion?
Yes. Well, if you don't have the propulsion, you can't. Going towards Moon L2 from the lower orbit, from a LEO takes 3.2 km per second. From a GTO can take 2.3, 2.5 km per second. So with current technology, it's
No, if you went with another mission, a bigger mission that was going to L2 already. So
oh yes,
like,
that would be nice actually, because you are already there. You go there. You have only to take care of your own station keeping, which takes 1 meter per second every orbit, more or less. So you can completely redesign the mission by, for instance, having water propulsion, which is safe. You can get rid of all of the green propulsion, and you can save a lot of space. For sure, you can even reduce from 12 to, I would say, a couple of minutes less. But that would be great, actually. Yes.
Thank you very much.
Thank you.